But in all seriousness, getting started now, yes, we're not going to go through the exam one today simply because we're still waiting on a couple students to take it. It could easily be because they don't have connection to internet, they're snow/iced in. There's a lot of things going on right now. So everybody gets a lot of latitude. Let's just, when in doubt, just be nice. Now, with that being said, those of you guys that took the exam, I am really, really pleased. The average grade on the individual exam, the group exam, and then the group take-home math all were solidly in the B range. So, on average, you guys are doing good. Obviously, if you hear that, then you look at your grade and realize that you don't like the way mathematically you're sitting compared to the average, that's fine. Shoot me an email. Be more than happy. We just need to find another way to approach the information so we understand it, because like anything else, we're going to be using a lot of the same stuff. Now, last week, we talked our way through chapter 7 and chapter 8. So when we're talking about assessing a skill, what's going on whenever we're talking about movement, as far as like how fast we're going to be, how we're going to break down our movement into those 4 phases. So our prep, or kind of then we'll go into our kind of wind up, then we have our force producing, then we have our follow through. So how you guys are going to go ahead and obviously figure out the angles on each of those like you did for lab 1. Now we just use time, because if we know time and we know the speed at which the angle changed, then we have a rotational velocity, which we're going to touch on a lot more today. Along with, if you know the change in velocity over the change in time, now we've got the acceleration that limb would have gone through during each of those phases. And since you've got those, if we know the length of the meter, which I know one of you guys was able to get that lab in, where we're looking at like the length of your arms, length of your torso. If you don't have access to a fabric style ruler, use a string and then use an actual ruler to figure it out. And then if you really want to try to ball on a budget, so to speak, remember a sheet of paper is 8.5 by 11. So we can fold this thing in half, fold it in half again, and then fold it in half one more time, and that's 1 inch, give or take a little bit. The full length being 8 on one side and then 11 on the other, and you can approximate using a pencil or a marker how long the string is in each direction that happened to be what was your dimensions or your lengths. So science. Now, angular motion is effectively how we're going to go ahead and move. So we are going to always be rotating about an axis. Okay, so what we're talking about here is how we're going to be in the golf example. You can see how we have rotation at our shoulders. You can see how we're going to also have rotation about the hips. You can see how the ankle is going to rotate. You can see how the arms, the elbow, might have a little bit of rotation, but not really that much. And then we're also going to have some rotation about the spine. And when we combine all those together, that's what's going to allow you to obviously drive the ball. So in this example, you can see from that wind up, so we've got our prep, wind up, our force producing till we hit the ball, and then our follow through. You can see how that club almost goes a full 360 degrees, where if we do something simple like putting, we're not going to have to go through anywhere near as large of a range of motion. Now, when we're looking at rotational forces, now we're talking about torque, okay? Torque is going to be the combination of force and then the moment arm itself. Now, the moment arm is based on what is known as the shortest perpendicular distance between the force's line of action and its axis that it's rotating about. So if we were to think about this simply with somebody using a wrench on a bolt. Now, we have a force. So notice it's a force of 20 pounds. Yes, I know it's not newtons, but just an example here. If we're holding the handle only a foot from the axis, we're going to have, effectively 20 foot-pounds of torque. And that's actually going to be how we look at it when we're looking at cars. So now, when we then compare it further down and we've increased that lever arm from being 1 foot to 2 feet, now we're going to only have to produce 10 pounds of force to still create that same 20 foot-pounds of torque. Now, when we say the action is equal to the perpendicular, what this means is we're looking at the line of force and how it's applied, and then how far that true perpendicular line of the force is going to be away from the object. Okay. What does this mean? Well, this is us using force vectors in the same way that we've used before, only now we're using these force vectors to actually look at the force of which it's actually going to be putting at that axis. So if we're looking at these forces here, we have the force going about the rotation. Good morning, Tinks. Sorry, the cat is needing my attention because she's always neglected. And from there, we're going to have the line of action of that force, which is, notice part of it is going to be going away from the joint or from the axis, and then part of it is going to be going perpendicular to that force production. Now, the examples that we're going to use in the class, we're going to make it relatively easy for you guys to discern where these angles are at, but just understanding, if you go ahead and put your hand on your desk so it's facing straight up and down, okay? From here, I'm going to push force straight down into my hand, and it takes really no effort to keep my hand where it's at, okay? Now, if I go ahead and put my arm so it's in a lengthened position, okay, and I do that same situation if I push down, I don't have to apply near as much force to go ahead and get my hand to flatten out. Now, we're applying the same amount of force, whether we're going straight down into it or if we're further. But notice, guys, that perpendicular force, this is Tinks. She is a nice kitty. She was about to come and slap the laptop, which maybe would have caused a disconnect, which might make it a better morning for you guys, which, you know, tomato, tomato. But that's what we're talking about. We're looking at these effectual lines of that force production, because when we're pushing straight down into that axis, notice, guys, there's not a lot of force that's going away trying to push our arm and open that angle. So we're still pushing it straight down. The key is that force vector that we're looking at for its perpendicular is really small. But then when we get that arm in a lengthened position, it's going to become much, much bigger. So torque is going to be obviously that force that's trying to get us to rotate. And this is going to equal the magnitude of the force, so that's going to be newtons, multiplied by the length of the moment arm, which is going to be in meters. Okay? And remember, it's always going to be perpendicular.
I have to go to class. Torque.
What's up, Austin? How you doing there, buddy? And Austin has gone on mute. Okay, no worries, bud, no worries. So, it's okay. We're all getting through this together, guys. This is why I drink. It's tea, don't worry. I'm straight edge now, at least. Okay, so notice in this example, so this would be holding a ball, bicep is lifting it straight up. We've got the axis of rotation, which is the ulna, and we've got the force of this object pulling us down, okay? Bicep is going to be pulling relatively straight upwards. Now, if we were to go ahead and have the arm, instead of being in that 50-degree angle, we had it more in a 45, okay? Now, notice the ball's not going to be as far from the axis for that perpendicular force. So it's actually going to be a shorter or smaller amount of force going to be producing, okay? The bicep, because it's going to be in a slightly shortened position, that's going to change a little bit of muscle characteristics, but we're not getting there yet. And then the opposite is going to be true if we go ahead, or nothing, but somewhat similar if we're in a lengthened position and the arm in more of an extended position. So now, same thing, this ball isn't as far from that center of the joint, and so the force we're producing is not going to have to be as great. Now, whenever we have a balanced amount of force on one side of the lever to another, or an easier way to think of it is your force compared to your resistance, we're going to be in equilibrium. And a lot of the work that we're going to be doing is just going to be balancing these equations, okay? So what we have is 3 different classes of levers, okay? And a lever is just going to be a fixed bar that is going to rotate along an axis, okay? First class levers are effectively a teeter-totter. We have the force pushing down on one side and the resistance coming from the other. So this is going to be where if the force and the resistance are the same and the fulcrum is the same length, essentially, or it's set in the center, so we have got the same distance from that fulcrum is going to be the same, it should be in balance. Now, we then have second class levers, where we're going to have the fulcrum followed by the resistance, and then in the end, we're going to have the force. So a good example of a second class lever is going to be a wheelbarrow, where you're going to, the wheel itself is going to be the fulcrum, the resistance is going to be whatever you have loaded in the wheelbarrow, and then the handles that you hold is going to be the part that obviously you happen to be resisting. Finally, we have the third class lever, which is really how our body moves. So in the bicep example, we've got our fulcrum, which is our elbow, the bicep attachment, which is right into the ulna, and then we have whatever objects we happen to be picking up plus the weight of the forearm itself as the resistance. Now, this allows for a lot more speed and range of motion. However, it gives us a massive mechanical disadvantage, which we're going to keep breaking down as we go through. So that's all we're looking at when it comes to a lever. Obviously, it's to balance forces. If we're favoring that force production, we're talking about that second class lever, aka that wheelbarrow. If we want to go speed and range of motion, that's what we're talking about, the third class lever. And like anything else, it allows us to change direction to effectively what's the applied force. That's how we move. So whenever you stand up, you are rotating about your ankle, knee, and hip joint, which are all going to be overcoming the forces of the segments above them and allowing you to move. So remember, where the fulcrum is, where their effort is, and where the resistance is. It really only comes down to three different organizations of these concepts. Now, the key is where is the effort placed? Where is the resistance placed? That can change up your effective leverages a little bit, but in reality, it's just going to be variations on the same thing. So our bones are effectively the levers. The joints are fulcrums, and our muscles are going to be where we're producing force, and the resistance is going to get kind of difficult. So for example, let's think about the hip. When the hip is extending, okay, when you're standing up, what all is the hip lifting?
Our upper body?
Yep, yeah, good. So it's not just your torso, but what else? Yeah, your arms, your head, exactly. So it's lifting all of that weight, plus your clothing, unless you guys are currently not wearing any, which thank you for not turning your cameras on. That would make it weird for all of us, okay? It's lifting your jewelry. It's lifting anything you might have in your hands. So real fast, we're going to do what I refer to as ride the roller coaster. So if you're standing up, or you can kind of get out of bed so you can do this, all I want you guys to do is stand up, and we're just going to go ahead and push our hips back as far as we can. And then we're going to go ahead and stand it on up. I mean, you just feel how much resistance you have there. Okay. So we're lifting the weight of my torso, the weight of my arms, the weight of my ring, wristband, mustache, everything else. So now I want you guys to do the same thing with your hands down at your sides, like you're almost trying to do a bit of a bow. And you feel how difficult that really isn't. Okay. Now act like you're riding the roller coaster. So we have our arms nice and big overhead, and then come back up. And you probably felt how it's just a little bit more difficult there. That's because the center of mass of my arm has now moved up. So it's further away from that hip joint. And now that I've got that bigger lever arm, it's now in turn going to be much harder to do. So for example, it's not difficult for me to hold my little thermos of tea with my arm at length, because it probably weighs maybe 2 pounds. It's pretty full because it's very warm. But if I was to pick up that same cup using one of those grabbers that made it 6 feet further down, now that lever arm is a lot bigger, so it's much harder to go ahead and pick up and move. So that's when we're talking about the weight. Now, when we think about the antagonistic muscles, okay? So once again, we'll go ahead and do that bow. Why is it that I'm not headbutting my knees? What's getting in the way there? Why am I not headbutting my knees? Good, because of the length that they can move. So notice, guys, those are going to be the agonist muscles in that example, but they're not able to lengthen that far. Okay, fascia, which is going to be connective tissue, that's going to be limiting it. Also, another component is going to be straight up tissue. You know, if you meet somebody that's in really, really like insane, like yoga expert flexibility levels, they literally get hung up on their own body. You know, if I was to go and take and stuff like a massive pillow underneath my shirt, I would run into that pillow and I wouldn't be able to go ahead and flex any further because literally I'm hung up on myself. So there's a lot that's going on when we're getting into the body, understanding that's going to change your efficiency about your joints. And that's okay. But that's something that you're going to have to touch on a little bit whenever it comes to example. So we're always going to be in balance if our effort arm times our effort. So the effort is the amount of force we're producing. The effort arm is going to be its distance, remember, perpendicular to the axis equals the resistance times its resistance arm. And once again, based on perpendicular. So that would be that example of your elbow on the table, holding a weight with your hand, biceps pulling back. So we go ahead and have the shortest lever arm there, but it's already relatively short. But then we have the angle of that load. So if we wanted to make this example harder, okay, what would we have? How would we tilt? So we're not changing the angle that the arm is at, but we can tilt the shoulder. So we're leaning forward or leaning back more. Would we lean forward or lean back to make this harder?
Back.
So think about it. If we lean back, we're going to rotate it this way. So we're going to actually be shortening the resistance arm because it's now going to be coming backwards. So it'd actually be easier because your palm would be more flat up like we talked earlier. If we want to make it harder, we lean forward. So that way our arm would be more flat to the ground. So we would actually be lengthening this resistance arm. It's okay to look at this and be a little like, what? Like it takes a little bit of time, guys. And that's why we're going to keep talking our way through this, making sure that you guys understand this and doing a lot of examples. Okay. Let's touch on levers again. Only now let's think about where we find them in the body. Okay. A real simple example of a first-class lever in the human body is going to be actually your head. Okay. So when I'm standing in profile, my axis and atlas is here. Most of the weight of my skull is in front of that. So that means it's constantly pulling it forward. So the muscles on the backside are what's extending, keeping me upright. And so that happens to be where we have the resistance, or sorry, the force we're producing, our fulcrum, and then our resistance on the front end pulling us down, okay? Where we're going to see a first-class lever. You're also going to see it with the triceps because we connected the olecranon process, then we've got the elbow joint, and then we've got whatever we're trying to extend above it, okay? Now, you're going to see the same thing when we're using a pair of scissors. And this is going to be really useful as a means to accomplish a lot of different things. So if we're trying to balance forces, think about that teeter-totter. We just want to put that fulcrum somewhere in the center so that way the resistance and the force are going to be equivalent. If we want to make this better for force production, this is going to be like using a shovel in that you're going to put the shovel on the ground. You've got this long lever arm that you're holding on to. The axis the shovel is rotating at is the edge of the blade, and then it's scooping up the dirt that happens to be, or let's face it, snow in this condition, on the front side of it. So that's how we use this as a first-class lever, okay, in favor of our force production. If we want something to be more where we've got the fulcrum a lot closer to us, but we've got a lot more potential speed, this is, that example becomes a bit more complicated of what to do. So effectively, this would be if you're using like a long pole to reach something and you're using one hand to articulate it and the length goes along, where it's going to allow you to have a lot of speed and range of motion, but at the same time, it's not going to effectively be moving that quickly. This could be kind of like casting. If you just use your bottom hand to pull your hand towards yourself with a fishing pole. And this is a great way to change the direction of your applied force. So obviously, push down one side of the seesaw, other side goes up. Second class levers are always in favor of force. The key is how great of a difference. So if you guys go ahead and stand up on your toes, the ball of your foot is what your fulcrum is. That's where we're rotating about, okay? The resistance that we're overcoming whenever we do this is going to be the weight of our body. And so from there, the force production we're doing, the lifting, is actually going to come from our calf. So this naturally gives us a mechanical advantage to obviously getting ourselves on our toes. Now, you don't really find many other second class levers in the human body. That's pretty much it. Because you also, yes, you gain a lot in your force production. However, you are going to be losing a lot when it comes to your range of motion. Okay. We then have third class levers. Okay. This is going to be how we're really moving our body, how we're getting a lot of things effectively to occur. And that our resistance is at the end. Our effort is somewhere in between, and then our fulcrum or axis is on the other end. So you're going to see this from salad tongs to fishing poles to contracting your biceps to using nearly every single muscle in your body, in that we are going to be producing that force inside of the axis and the resistance that it happens to overcome. Now, this is good because it allows us to magnify speed and a range of motion. However, the longer the effort arm, okay, then the greater amount of resistance we're going to have to overcome. And so it's going to have natural trade-offs. Like, we're going to want to use longer lever arms when we're trying to throw objects. Whereas if you're thinking about trying to lift an object, say like you're trying to pick up somebody who's markedly heavier than you, you're not going to try to pick them up with your arms straight in front of you because that's a really long lever arm. You're going to try to hug them and pick them up, but this is COVID and social distancing, so don't touch them in the first place. Yay. However, understanding how this force production is going to give us advantages of speed, but once again, we have a trade-off. So we're going to be producing these torques along these different levers in order to go ahead and allow us to have all of our basic movements, okay? Where we're going to have the muscle itself is going to be lifting, okay? We're going to be then lifting the weight of that segment of our body. May it be the length in this example, or the weight of our lower leg. So we're talking about the shank or the shin, and the weight of the foot, and then the weight of the dumbbell that's strapped to the leg. If I catch any of you doing this exercise, I will make fun of you because it's dumb. But it's a good example in that we've got one load here, the load of the foot and the shoe, and then the load of the shank, all of which has to be overcome by the hamstring itself. So we are in equilibrium if our effort equals our effort arm, or sorry, effort times our effort arm equals our resistance times our resistance arm. Okay. Now we can have multiple resistances. So in that previous example, the effort is coming from the hamstring. The effort arm is where the hamstring inserts. Then we have the weight, so multiplied by gravity, so that's the force of the lower leg multiplied by the center of mass of the lower leg. Then we have the resistance of the foot and the shoe multiplied by the center of mass of the foot and the shoe. And then finally, we have the resistance force of that dumbbell multiplied by its center of mass from the axis. So we actually have three different ones we need to add together on the one side. So in this example, you're gonna need a lot more force to overcome that set resistance, but notice we can get from the same amount of degrees, but the distance we're going to have actually displaced is gonna be much, much larger. Now, the other thing to keep in mind is when we're looking at rotational force is what's known as this eccentric force, okay? So this is not gonna be in line with the center of gravity. So we're gonna have both rotational force and translatory motion, okay? Now, this is going to, in turn, cause that object to rotate somewhat, even if it has a fixed axis, and then it might cause it to move as well. So what this effectively means is as we're trying to pick up or move objects, we're going to get them to rotate. So if you're trying to, like, if you're doing tire flipping, the center mass of the tire isn't the dead center of it. However, you're going to cause it to rotate about the axis on the far side of the tire while you're picking up the one side. Then we've got two people who are failing to social distance and they're holding hands and leaning back. I don't know why, but it's an example you can think of. But then also look at somebody throwing a spiral of a football. So something that Tim Tebow can't do, but Tom Brady can. So when you're going to go ahead and throw the ball, you're giving it both a linear and a rotational force, and that's what's causing that spiral to occur. Now, another great example of this is if you're looking at the sport of football, or you're just trying to walk around right now on the ice, in that when your feet go out from underneath you, it wasn't like, it'd be fun to fall on my butt because it's slick outside. Instead, what's happening is we've got a lack of coefficient of friction. We've applied force into the ground, and since it's off and outside our center of gravity, what friction can handle, it's going to in turn cause that force to quickly rotate our body. Now, the problem is when we've rotated our body and now we don't have anything underneath us, we hit the ground. And you can also see this whenever people are playing football, rugby, something where they get tackled. If they take that hit in their knee, if they take that hit in their upper body, you see their body actually spin, because notice they're going to go and rotate about their center axis. Whereas if they take the hit directly in their hip, it tends to drive their entire body in whatever direction that force was produced. Now, every joint is always going to move according to the summation of those torques. So when we've got two or more torques together, this might cause us to not move. This might cause linear motion. This might cause rotation. So if they're going to be in parallel and they're equal to the balance seesaw, we're not going either direction. However, if they're parallel and overcoming that resistance on both sides, so example, think swimming, think canoeing, that's going to allow us to have a basic linear motion, okay? And we're going to also naturally use what's known as force coupling. And this is where we're going to have multiple muscles that contract at the same time to cause rotation. So our external obliques pennate forward. Our internal obliques pennate backwards. So whenever I turn to the right, my external oblique on my left side is firing and my internal oblique on my right side is firing, and that's what allows me to rotate. When I lift my arm overhead and get that upward rotation of the scapula, my trap 2, my lower traps, and my serratus anterior are all going to contract, and that's what's going to allow my scapula to rotate as we're moving upwards. So we're going to see this also when it comes to things like internal and external rotation, is that we're going to have muscles that are contracting on both sides of the body, which in turn is going to allow us to move. So how much torque we have in the system is always going to be equal to the sum of all these individual forces put together. Okay, so every torque has both a magnitude and a direction. So when we think of it, it's going to move us clockwise, that's going to be considered to be negative. Counterclockwise is going to be positive. So if we're going to look at the summation of torques, so we have our fulcrum represented by the triangle in the center here. We have a force lifting, a force pushing down, and a force pushing down. Now notice overall, this is going to have a negative amount of torque. Okay? How do we come to this conclusion? Well, we're going to take and put together each of our individual torques and solve them all together. Okay? So we have a negative 5 newtons right there, multiplied by 1.5 meters. So that gives us the torque there. We then have, because once again, this is going clockwise, a 3 meter lever and 10 newtons there. So our negative torque is going to be 37.5. Then our positive side, because it's moving us counterclockwise, excuse me, is going to be 5 newtons multiplied by that 3 meters, because yeah, it's 1.5 from the axis to A, and another 1.5 from A to C. So it's going to be 3 meters altogether. So when we put all these together, that's going to give us our total torque, which is going to be negative 22.5, which means that as soon as we would hit and start or allow it to go, we'd see this rotate. Now, one thing to keep in mind when we're looking at these angular motions, notice the speed and the range are going to be interdependent, meaning one depends on the other, okay? So if we literally go from essentially this start angle to this, so start angle of 0 to this finish angle, which says 30 degrees, if we had an object attached to B and we were to measure the distance it's gone, it would not have obviously gone anywhere near as far as an object that happens to be all the way down at where C is at. Now, both have traveled the same amount of degrees. The key is that total range. So there's a big difference in how far an object has gone if I'm just curling it with how long my arm is to lifting it with my arm straight. We've moved the same amount of degrees at each of those axes. The key is we have a much longer limb when we put the entire arm together. And everything we're trying to do with moving the human body, guys, is literally just trying to solve a problem. That's it. We're trying to use effectively our body to solve a physical problem. And the body's trying to solve it as efficiently as it can. So it's only going to try to use effectively only the levers that are necessary, and doing so with as little energy needed as possible. So right here, guys, we have an example of rotating about an axis. So it's also if you're holding an object. Turns out you're going to be rotating much faster if you keep that object in closer to your center of axis. Think about like a figure skater spinning at high speeds, where you're going to naturally see them pull in and go tighter in their body midline, as opposed to when they're trying to slow down, they're going to extend their body. And that's going to be fun because we're going to get into angular momentum a little bit later on. So what we're going to see is the body is not always going to use the longest lever arm. Instead, it's going to use what happens to be the best in given those situations. So, for example, if we were going to go ahead and throw a ball, yeah, pulling back, really extending the shoulder and going fully through is going to give you a much greater velocity, but it takes more time. Whereas you could instead say this basketball, just chest pass it quickly, and you're going to get that ball out of your hands at a much faster rate, even though your maximal velocity is not going to be as great if you do that larger windup and otherwise. Now, when we're talking about, say, lifting weights, you're not going to deadlift something that happens to be really far away from you. Instead, you want to make sure that weight is right over your center of gravity, so we shorten the levers of how far we have to effectively lift that object as much as possible. That's a big component of the sport of powerlifting. And if you guys want to see some ridiculous examples, you can look up videos of people that have an excessively large bench arch, because then they don't have to move the bar as far, because it turns out you have very little range of motion. So meaning bringing the bar down, touching the chest and pressing it back up. If you happen to have a real big arch where you barely have to move, you might hardly even have to unrack and move that bar, much less taking a wider grip, so you can really shorten your range of motion. Now, these levers are going to give us what's known as a mechanical advantage. So it allows us to magnify the force of which we're producing. So what we're really looking at is the ratio of the resistance to the effort, and that's our mechanical advantage. Or we can think of it as the effort arm compared to our resistance arm. So think about mechanical advantages when you guys are using tools around the house. What would be some examples you would use that's going to optimize your effort arm compared to your resistance arm? to make it easier to do something.
I had to attach a wrench to the handle of a screwdriver to be able to turn a screw tighter.
That is a great example of it. Of now you've got that lever arm of the wrench as opposed to just trying to rotate the screwdriver. Same thing about using a longer wrench handle in order so you can go ahead and give yourself that mechanical advantage whenever you happen to be trying to use a hand tool. Absolutely. So we're going to use things all the time to give us a mechanical advantage whenever we happen to be trying to do it. If any of you guys ever had the chance to see farm tools, like meaning wrenches for working on tractors, yeah, exactly. Where you're talking about the handle can be 5 feet long. And I've even seen people use like aluminum fence posts where they'll put that on the end. So now they've got like 8 feet to go and rotate, because remember guys, torque is Newton meters. So the longer we increase that meters for the actual length of where we're effectively trying to rotate about the axis, the smaller amount of force we're gonna have to use to break those bolts loose. So now if we were to look at this like sport, and this is where if we had you guys all together, we could take advantage of this. Any of you guys ever watched arm wrestling or done arm wrestling? So one of the basic moves is what's known as the top roll. So, hey honey, can you hear me? My wife is off from work today because she's obviously not driving our very sensible family sedan of a Honda Civic through the wonderful snow that we have up here in Lexington to go to Nicholasville. Okay, so if I'm going to be arm wrestling, I guess myself now, okay? And so we're gripped up. I know this is incorrect. The top roll is where you're going to go ahead and rotate and pull your wrist in towards you. So now what you've done now is I've shortened that lever arm from the angle of my elbow to the end of my hand. And by doing this, it's going to put me in a stronger position. Now, for my opponent, because I've just rolled them over, so if we show that from the other side, I've now lengthened the lever arm for the other person, giving them a mechanical disadvantage. So we're utilizing things like this in sport. That's why in like wrestling, trying to get someone in tight and really get them in close to your shoulder, because we're a lot stronger closer to our joints than we are obviously with our arms in a long position. Hence the arm bar. You put somebody in an arm bar, it's very rare you're going to find somebody whose single bicep is stronger than the entire lower body of the other person. And if it is, that's not a human being that I would want to fight. So anytime that you guys are going through your project, you need to think about, okay, where's the fulcrum, the effort application, and the resistance application. So for your joint, there's your fulcrum. The resistance is going to probably be the weight of all of the body segments that happen to be being moved above that joint. So if we're looking at the knee and we're doing a vertical jump, okay, the knee has to lift the center of mass of the thigh, and then the center of the mass of the effectively all of the weight going through the body through the hips. Okay, now this is being lifted in the extension concept by our quadriceps. Okay, now what's the angle? That's why we did that goniometry lab, so you can figure out what's the angle at that joint. Okay, what is the angle of the resistance applied to the lever? So if we're going to look at the knee example, we've got the quadriceps that's going to be shortening through the patella and the patellar tendon. And then obviously, how long is that effort arm? How long is that resistance arm? Okay. Now remember, the resistance arm, we have the center of the mass of the thigh. So we've got the mass there and the distance that is from the knee joint. And then we have the center of the mass of everything above, which is going through the center of the hip. Okay. So from there, we are going to think about, okay, what type of movement does this favor? Well, are we talking about, in this example, we've got extension and we've got flexion, but if we're looking at the hip, we're looking at the shoulder. Now we've got internal, external rotation, horizontal, AB and adduction. We have got our central flexion, extension, or sorry, abduction, adduction, and then flexion and extension. So we've got a lot of different angles we can move in. Okay. What is the mechanical advantage or the disadvantage? and what class lever we're working with. So in the shoulder, in the hip, we're really talking about pretty much exclusively third class levers. Whereas when we're looking at the knee, your quad is technically getting closer to functioning like a first class lever, because remember, it's going to go patellar tendon and patella. Then we've got our fulcrum, that is our knee, and then we've got the resistance of everything above it. So all of these things are going to be important for you guys when you're obviously working on your projects of making sure you understand how all these go together. So in the chat, guys, go ahead and put up what group you guys are in. I am going to go ahead and have you guys go into breakout rooms with your group members. And from there, we're going to allow you guys to go ahead and work together on breaking down each of these things. And so it can get to be obviously pretty difficult. Okay. So I'm making sure I do this right the first time. Rock and roll. Okay. So go ahead and head on in those rooms, guys. It's 10:13. We're going to plan on coming back closer to about 10:20. I want you guys to think through what was those angles that you've got at each of those points. You're going to go ahead and talk your way through, obviously, your joint, what all your joint is lifting, and then what muscles are going to be providing that force production to overcome that resistance. Okay? So help each other out, talk through your motion, think about what's going on, because it's going to change phase by phase. Sometimes the muscles are going to be working eccentrically, sometimes concentrically, sometimes not at all. So whenever you're ready, guys, go ahead and hop in those groups, and I'll see you guys back at 10:20. Yes, because that's going to be part of your assignment, is to break it down during each of those phases. Okay, so now we go back hard into the math, guys. Okay, so when it comes to Newton's laws, where we've got our wonderful objects in motion stay in motion, well, now it's the same thing, only it's rotating about an axis. The acceleration of the rotating body is directly proportional to the torque causing it. Okay, same direction as the torque and is inversely proportional to the inertia. So now it's what it's acted upon. Yes, we can definitely work through a joint together. And yeah, when torque is applied to one body to another, the second body will exert the exact equal and opposite torque on the first. Hooray! It's just the same thing, only now it's rotation. And since we've got a gold star attendance day, meaning we've got barely over 50% of the class in here, I'm okay with us not really going into the torque and the rotational formulas too much, because it's It's good stuff. It's just obviously not easy. So, okay, we want to work through a joint together. Give me a movement and we'll go ahead and break it down. Free throw. Ethan, I can't help but notice that's your group. Funny how that works. Okay. So, hurdle jump. No, it's okay, guys. It's okay. All right. So let's go with the hurdle jump. Okay. We're going to say it's going in just to jump over a hurdle. So preparation is just standing there. So we'll go with the hip joint. So you're going to be using your glutes, your hamstrings to keep your hips pretty extended. Your degrees are probably going to be about 180. Then you're going to go ahead during your wind up, you're going to bend at your hip. So your hip might even go all the way to a 90-degree angle. And that's going to be eccentrically lengthening our glutes and our hamstrings. Now, from there, we're going to go to the force producing, where we're going to go ahead and extend the hips aggressively to that 180 degrees again in order to jump up off of the ground. But now we've got an interesting little addition because we're jumping over a hurdle. So once we extend the hips all the way, lifting the upper body off of the ground, okay, so all the force there, we're going to be airborne. Now, once we're airborne, we're going to use the hip flexors. So that's going to be our tensor fasciae latae, our rectus femoris, our ilius, and our psoas to lift our knees up. So we're going to be in a tucked position to get over that hurdle. Now, once we clear the hurdle, we're going to use our glutes, our hamstrings to extend our hips a bit or close to extended. And then as we hit the ground on what would be the follow through effectively, we're going to eccentrically contract the glutes and the hamstrings to absorb ourselves into the ground and obviously just not land peg-legged, which is a great way to make all of your joints hate yourself. Okay. So if we're going to look at that same movement, and now we're going to go with the knees. Okay. Wind up, or sorry, our preparation, we're standing there, knees are extended. We're then going to wind up. So we're going to go ahead and bend those knees, squat down. That's going to be an eccentric contraction of our quadriceps. Okay. From there, we're going to extend them into a concentric contraction of straighten our legs violently, which is going to be lifting not just the thigh, but the entire hips and everything above from the torso, arms, head, etc. Now, when we're airborne and we are going to be pulling our heels to our butt in order, so we're tucking our body in, that's going to be a concentric contraction of our hamstrings, which will be the bicep femoris, the semitendinous, and semimembranous. And once we clear that, we're going to use the quads again to extend the knee. So that way, whenever we hit the ground, we can eccentrically contract the quads to absorb force on the landing. Does that make sense to you guys? I'm not getting a strong vibe that it made sense. Yes, I think so. That's okay. That's okay. Okay, okay. All right, so let's go back to the beginning where we're talking about the hip, okay? Oh, actually, I think I know what I want. I want you. Okay? I'm sorry, guys. Now you have to see how great of an artist I am. Okay? So we're going to start off pretty much standing. So the hips are at 180 degrees. The knees are at 180 degrees. No, they do not have like a tumor on the back of their leg. So then we go to the bottom of the movement. Then again, we're going to aggressively be extended. So we've got the ankle, the knees, the hips. Then we are going to go ahead and be in a nice tucked position. So ankles, knees, hips, and then we're going to go ahead and land Did I tell you my sister has an MFA? All right. So we're going from the one to the next to the next. I'm also left-handed and drawing with my right hand, so we're going to be very generous right now. Okay. So if we're going to look at the hip joint, so when we're standing here, the hips have to hold up everything above. So we've got the weight of the torso, we've got the weight of the arms, we've got the weight of the head. I am very happy that my little sister can't watch these classes live because she would just rip me a new one. Okay, so it's going to be extending, because notice the lever arm, so the resistance arm is really tiny because we're looking at that perpendicular force. Okay, and so right now it's hardly anything because nothing's bent. But now as we're bending forward, okay, from the hip joint, we've got the center of the mass of the torso. We'll say that our arms are here. So we've got the center of mass of the arms and the other arm, and then we've got the center of the mass of the head, which all of those have to be equated because that is what's being overcome by those glutes and those hamstrings. Okay, so all of this is pulling us down. So if we're going to look at the lever, we'd have a lever that goes out, you know, here's the one, here's the other, here's the other, here's the other, and then effectively on the other side of the lever, here's the fulcrum. There's my mediocre triangle. I'm actually not trying to draw it in, I'm just bad at this. Okay, all that's pulling us down, but then we've got the glutes pulling with enough force to extend all of this. Okay, so the eccentric, this force will be smaller because it's just absorbing. And then on the concentric, it's going to be massive because we're trying to really extend through the hip and lift all these parts of the body. So now, once we're off the ground, okay, so we've extended all that force, the lever arms are short. Now the hip flexors on the other side are going to be lifting up the legs. So it's going to be lifting up the center of the mass of the thigh, the center of mass of the shin, and the center of the mass of the foot. All of those, if we're going to draw our little example here, we've got the hip flexors pulling upwards hard. Then we've got the center of the mass of the thigh pulling us down, the center of mass of the foot pulling us down, and the center of mass of the shank pulling us down. Okay, and so now once we've landed, okay, we are going to eccentrically be absorbing that force of the torso, the arms, the head itself. So if we were to draw it out again, we'd have the forces here, 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 fulcrum, and then the force of the hips from allowing us to just slink over. How's that going? Is that a kind of a better walkthrough? Does that make a little more sense when I draw it out like that? Okay. Yeah. So that's what I want you guys to do with your joint in your phases of the movement. Okay. Where we're going to be breaking down each of those parts, and you're going to be looking at, okay, here's what I'm going through. Here's the forces that I'm encountering because I've got the weight of that, whatever segments of the body or the object that you happen to be lifting. If we're talking about if we're doing this with, say, a deadlift, okay, now we've got the weight of that barbell that also is going to be really pulling us downwards. That magnifies obviously the force that our muscles have to produce in order to lift. So we've got to look at the weight on the object, how that's going to translate through the center of gravity and the length of those lever arms, and how we're going to organize it all together. Sorry, my sinuses are going a little berserk this morning. Don't worry, it's not the Rona. Okay, so it's 10:32. Good job making it here today, guys. And this is not an indictment if you're watching this later, because obviously, you know, we've got quite the winter storm, and depending on where you're at, you could still have issues with power outages or no connection to the internet, which that's got to have its own challenges. So you know, stay safe out there, guys. Make sure you stay warm, and do yourself a favor. I'm going to let you guys out early today, but I want you guys to think about and try to draw this out with your own movement, okay, with just your joints, and try to think about, okay, what are the segments that we have to lift? Because we can figure out the weights of these segments, because they're all going to be based upon how heavy the person is. And I have some examples up on Blackboard of some easy formulas you can use to kind of figure out your average person arm weighs this percentage of their body mass. Your average person hand weighs this percentage of your body mass. So you can, if you know the body mass, you know gravity, now we can derive force. And then from there, you can figure out how fast you're moving and divide, also figure out the torque, because we've got the length of the lever arms, which you guys are going to be doing for lab 2 if you haven't done so already. Okay. So we'll let you guys go early. Make sure you guys go through this stuff, stay safe out there, and yeah, have a great day. Is there any other questions you guys would like me to answer? It's okay if you don't think it's fair that I'm letting you guys out 11 minutes early. We can always do more lecturing if you guys would like. I just feel like we're kind of hitting a good point today to kind of call it. All right, well, since not seeing any comments, stay safe out there, guys. Take care of yourselves, and I will see you guys again sometime soon. So, bye-bye.